All right, so question number 6. Again, the first step is to factor out the GCF. So looking at our numbers, the smallest number is 2. 2 goes into all of them. Therefore, 2 is a GCF. X to the 4th, x squared, nothing. So we're going to be left with x to the 4th plus 11x squared plus 30. Okay, the next step would be to list the factor pairs for A and C. But this guy actually falls under what we did the other day, where A equals 1. I have a trinomial, technically of degree 2, because remember that's x squared squared, and leading coefficient of 1, so you can actually go back and do x method instead of doing guess and check. What multiplies to be 30 and adds to be 11? Go through your factor pairs, so 1 and 30, 2 and 15, 3 and 10, 4, 5 and 6. Okay, and it is 5 and 6. What kind of 5, what kind of 6 add to give me a positive 11, a positive 5, and a positive 6? Therefore, bring down your GCF. Don't forget, if you ever have this weird variable stuff, usually the middle term is kind of a hint, but you ask yourself, what times what is x to the 4th? Well, x squared times x squared is x to the 4th, and that's how you get that x squared term in the middle. And now I have a positive 5 and a positive 6. So I'm going to go ahead and box that off and just double check. I'm going to check my inner outer product. I got 5x squared. I've got a 6x squared. 5x squared, 6x squared gives me a positive 11. Positive 5 times positive 6 is a positive 30. So I've checked everything and it looks good. Okay, so on to the back, we're going to talk about some special products. The first one is actually going to be difference of squares. We've actually seen this difference of squares back in 11.3. We gave you two binomials with the same numbers with different signs, and you knew the pattern was just to square the first, square the last, and tag on a negative in the middle. So now we're going to go backwards. We're going to factor that. So what you're going to do is if you have a difference of squares, so first word of that meaning difference, it has to be a subtraction symbol or this will not work, and I'll prove that in just a minute. But it's got to be a difference, and then it has to be squares, two things that multiply by themselves, whatever, to give you that value. So y squared is y times y. 9 is 3 times 3. So I have a difference of squares. All you're going to do is do your two parentheses. I know it's in the form a plus b, a minus b, so it's the first term. So y times y is y squared. 3 times 3 is 9. And I've got to have a plus and a minus, and that's it. I'm just going to show you one time real quick why this is true. So if I do my inner product, I get a 3y. If I do my outer product, I get a negative 3y. So the reason this works is because this positive 3y and negative 3y end up canceling each other out, so you have no middle value. So that's why you have to have a positive and a negative. And we know that a positive times a negative gives me a negative number. That's why this has to always be a negative, a difference of square terms. All right, so moving on to the second one. Again, the first step is always check for GCF. Well, does 4 go to 25? No. Does 2 go to 25? No. So there is no GCF on that one. But how do you get 4x squared? Well, that's 2x times 2x. How do you get 25? Well, that's 5 times 5. Double check it's a difference. It is. And you literally just plug them in. 2x, 2x, 5, 5. Make one plus, make one minus. Does not matter which order you write it in. And that is it. Difference of squares problems are the easiest to spot because they're literally difference of squares. It's in the title. And the easiest to answer. Okay, moving on down to number 3. Again, check for GCF. So I always check the smallest number first. And does 16 go into 64? Well, actually, yes, it does. So 16 is my GCF. There is no x GCF because there's no x in that last term. So divide each term by 16. 64 divided by 16 is 4, leaving me an x squared. And then negative 16 divided by 16 is a negative 1. So now, do I have a difference of squares? Yes, subtraction. And even though it looks confusing, but 1 actually is a square because 1 times 1 is 1. And then again, we have this 2x, 2x thing. So bring down your GCF, do your two binomials. The first term, 4x squared, comes from 2x times 2x. My last term of 1 comes from 1 times 1. Make one positive, make one negative, and that is it. Okay, last one. Again, I'm going to check for the difference of squares. Difference, check. Uh-oh, these are not squares. But Maybe when I take the GCF out, it might be squares. So does 3 go into 48? Yes, it does, leaving me 3. Divide here, you just get m to the 4th, minus, and then 48 divided by 3 is 16. Okay, so now do I have difference of squares? Well, I have a difference. 16 is a square, because that's 4 times 4. Is m to the 4th a square? Well, can I multiply the same thing by itself twice to get m to the 4th? Well, yes. M squared times m squared. So I have a difference, and I have some squares. So bring down your GCF, do your two binomials. How do I get m to the 4th? Well, that's m squared times m squared. How do I get 16? That's 4 times 4. Make one plus, make one minus. Normally, you'd stop here, but, and they do this on the EOC sometimes, is check for difference of squares again. I see a difference, I see some squares, I can actually go one step further. Kind of run out of space, but I'll squeeze it in here. Okay, how do I get m squared? Well, that's m times m. So here's an m, here's an m. How do I get 4? Well, that's 2 times 2. So plug in a 2 there and a 2 there. Make one plus, make one minus. I kind of wrote too big, that's okay. My final answer is actually this. I had a difference of squares hidden within another difference of squares. So whenever you're doing these problems, and actually any problem from now on, if you ever have a binomial subtraction in it, if you have some sort of squared left over, I would always check for difference of squares that may go down one step further. This does not break down because it's not a difference of squares, it's a sum of squares. And that doesn't do a thing. You just leave him alone. This guy does break into two parts. Our next pattern is perfect square trinomials. We actually also saw this pattern in the other order in 11.3. In 11.3, I gave you some binomial squared, whether it had a positive or negative on the inside. And we learned, hopefully, that the pattern was to square the first, square the last, and then multiply them together, and then double it or multiply by 2. And there were two separate formulas, because whatever sign was on the inside is the sign that matches that first sign in your problem. So this plus tells me it's a plus here, this negative tells me it's a negative here. Okay, so these guys are not as obvious as the difference of squares problems, but they're still pretty easy to spot. You're going to check the first term as a square. Well, how do you get x squared? Well, that's x times x. Check that your last term is a square, 3 times 3. And then check that your middle term is 2 times your first times your last. 2 times x times 3. 2 times 3 is 6 times x is 6x. If this has a perfect square trinomial pattern, you can go straight to the answer, and it's just the first term, the last term, and it matches the sign. First term is x, last term is 3, and because I have a plus sign, I'm going to bring down a plus sign, and just square it, and you're done. This will actually be how we want our answers written with the squared there. You could also solve this guy, of course, by doing the x method. So what multiplies to be 9 adds to be 6. Well, that's a 3 and a 3, positive 3, positive 3. You would have done x plus 3 times x plus 3. Still the exact same answer. This took less work if you see the pattern, but also we do want the same thing written twice to be written one time with a square as the exponent. Okay, going down here to question 6. Again, you'd always check for GCF, but there's no GCF in this problem, but that's always the first step. So 49x squared is 7x times 7x. So I've got a perfect square starting it, 1 times 1, perfect square ending it, and is the middle 2 times the first times the last. Well, 2 times 7x is 14x. It does. It does have a negative sign, and that just tells me I'm going to have a negative sign in my answer. Take your first term, 7x, take your last term, 1, square it, and you are done. These guys are very easy if you learn the pattern. Our last section is factoring trinomials with two variables, and that's going to be when you have some extra variables hanging around that's usually not in the beginning. You're going to follow the exact same factoring rules, except just pay attention to your extra variables. So this guy, he's a trinomial with leading coefficient of 1, so you actually could do the x method on this guy. Just ignore the variables for now. What multiplies to be 4 and adds to be a negative 4? Well, that's going to be a 2 and a 2, a negative 2 and a negative 2. When you're writing it out, though, just be careful. How do I get my first term? Well, that's x times x. How do you get your last term? Well, my last term comes from -2 and a -2, but I have a y squared on there, so just tag on a y. That's literally all there is to it. If you want to check your outer inner product, you can. I'm going to go ahead and do that real quick just to prove it. -2y times x is -2xy. Outer product is also a -2xy. Those give you a -4xy. By adding that y on there, you've now got your y squared and you've added a y into that middle term. Also, we didn't do it this way just because I wanted to show you the process. This guy is actually a perfect square trinomial. So he is x minus 2y squared. So I don't care how you get it, whether you get it by doing the perfect square trinomial pattern or you do it this way. If you see it's the same answer twice, though, in the end, I do want your final answer to be written like that with the squared. All right, same thing on number 9. Number 9 is a trinomial with a leading coefficient of 1, so I can go ahead and do the x method. What multiplies to be 5 and adds to be a -6? Well, the only factors of 5 are obviously 1 and 5. And how do I make it be a -6? Well, I'm going to add a -1 and a -5. So when writing your answer out, how do you get y squared? Well, that's y times y. But how do you get z squared? Well, that comes from z times z, and just tag on your numbers, -1 and -5. Doesn't matter if you add your variables at the end or beginning. In the end, -1z times -5z is going to give me a positive 5z squared. If I check my inner and outer products, I'm going to have a -1yz and a -5yz together, giving me a -6yz. We don't normally write a 1, so I'm just going to write that again. It's y minus z and y minus 5z. And that's your final answer. All right, on number 10 here, we're going to go ahead and go through the process. So ignoring the fact that there's a y squared there, we're just going to do all the stuff like normal. So step 1 is always check for GCF. Smallest number is 2. 2 does not go into 3, therefore there's no GCF numerically. Check for variables, well, there's x squared, x nothing, y squared, y nothing. So there's a whole bunch of variables, but none that are in common, so no GCF. Next, it's not a difference of squares, so it's a trinomial. But I don't have a leading coefficient of 1, so I cannot do the x method, so I have to do factor pairs of the first term and factor pairs of the last term. And then we're just going to guess and check. So, setting it up, how do I get 3x squared? Well, that's 1x times 3x. Then how do I get 8y squared? We'll just do your normal guess and check. So I'm going to plug in a 2 and a 4, just because I always pick the closer together numbers first. Check your inner product. We got a 6x, outer product, 4x. Ooh, this is nice. How do I make 6x and 4x give me 2x? Well, I want a positive 6 and a negative 4. Again, the inner product goes here, the outer product goes here, but don't forget your y there. You're literally just going to add that y to each of those spaces. I probably should have left a little more space there, but let's go ahead and write it out nicely. So x plus 2y and 3x minus 4y. Let's just double check real quick. Does positive 2y and a negative 4y give me a negative 8y squared? Yes. We've already checked our inner and outer product, and we already chose our first terms to give us 3x squared. So this guy is correct. All right, number 12. Again, step 1 is check for GCF. 2 doesn't go into 9. There's no common variables, so there's no GCF. So I'm going to go ahead and list my factor pairs for my first term, because it's not a 1 and I can't do x method, and my factor pairs for my last term. I'm just going to go ahead and guess and check until I get it right. I like to pick the closer together ones again, so 2 and 5, and I'm looking for an a squared, so I need a times a. Then I'm just going to guess 1 and 2 or 2 and 1, doesn't matter. Inner product 5a, outer product 4a. Oh, sweet. So I want a negative 9a. So how do I make 5 and 4 give me a negative 9? Well, I want a negative 5a and a negative 4a, but I really don't want an a, I want an ab. So don't forget to literally just tag on those b values. Just tag on a b and tag on a b. Negative was my inner product. Negative is my outer product. Just going to write that again. 2a minus 1b and 5a minus 2b, and you're done.